So, we have been discussing about the pearlitic transformation in steels, and I showed you that if we cool down austenite from high temperature to below 727 degrees Celsius at a very slow rate, austenite transforms to pearlite, which is a mixture of ferrite and cementite. And this is very evident from the phase diagram itself. As you see here, there is a eutectoid reaction at about 727 degrees Celsius temperature for a carbon concentration of 0.8% carbon. And this transformation actually leads to formation of alpha plus Fe3C. So, that means carbon get partitioned between alpha phase and a carbide, which is known as cementite. And this happens when you cool the sample slowly. That is because this is a diffusional transformation, and important species which partitions between the phases is the carbon, and carbon diffusion requires time. Therefore, if we cool it differently, the phase transformation will be bypassed and something else will happen, and that is the basic purpose of discussion today. What are the things which can happen? And I have pointed out that if you quench the steel from 950 degrees Celsius temperature, then it will lead to formation of a new phase called martensite, or otherwise if we quench the steel to an intermediate temperature at about 400 degrees Celsius temperature, then it leads to, in an escape long time, then it will lead to formation of a new phase called bainite. So, therefore, depending on the type of heat treatment, it can lead to different structure. By the way, pure iron has a polygonal structure as you see here, and this is normally body center cubic magnetic iron. When we add carbon, we start seeing a lot of interesting stuff. This is the first thing I showed you, that if austenite is cooled below 727 degrees Celsius temperature, it will lead to formation of Fe3C, which is shown as a black color or grey color phase, and alpha, which is known as alpha Fe. Basically, it has almost no carbon, therefore, it is almost like a pure iron, and the interface looks like a very carved one between the gamma and the product phase. And we discussed a lot about these, so let us not do that. But you know, we always have hypo or hypoeutectoid steels, which will also transform into pearlite, but it will transform into something else plus pearlite. So, if it is a hypoeutectoid steel, you can have ferrite as a primary phase. That is obvious from the phase diagram. Let us not discuss again the same stuff, but if it is higher than 0.8% carbon, it will lead to hypereutectoid steel. Therefore, the primary phase will be cementite. So, first let us look at how the ferrite forms, because this ferrite which is forming above the 727 degrees Celsius temperature is known as a primary or pro-eutectoid ferrite. So, these ferrites can have different kinds of morphologies, and that is actually dictate the mechanical properties of the steel, because as you know, most of the steels are actually mild steels. That means the carbon concentration varies from 0.4 to 0.6 weight percentage. So, they are basically hypoeutectoid steels. So, if hypoeutectoid steels are produced in large quantity, we must know what is their microstructure. As you know, the phase diagram tells you that the carbon concentration less than 0.77 or 0.8, whichever is you take, does not matter, it depends on the type of books you read, but it is basically 0.77 weight percentage as far as the phase diagram is concerned. So, it is less than 0.77 weight percent carbon, then it will lead to such a kind of ferrite known as allotriomorphic ferrite. As you see on the both side, you have certain kind of a pearlitic morphology on the grain structure. Or you can also have what is known as Wittmann-Statten ferrite. Wittmann-Statten ferrite is named again by the scientist known as Aloyd Wittmann-Statten. This is actually plate-like structure. As you see here, there are two grains as I mark, this is gamma 1 and gamma 2 initially, and then on this is the boundary. So, the ferrite which was nucleated on the boundary had a orientation relationship with the gamma 1. that is why the interface remains flat, and it grows into the gamma 2 grain with which it does not have fixed orientation relationships, and these plates are actually growing very rapidly into the gamma 2 grain. That is what is observed from this picture. Such a kind of morphology is known as Widman-Stratton ferrite. There is another type of ferrite which is very rarely observed, is known as idiomorphic ferrite. So, it can form inside a gamma grain, which is very rare. Basically, nucleation of the ferrite will always happen at the grain boundaries, as you know, because grain boundary, grain corners and grain edges are the best nucleation sites for the heterogeneous nucleation of the ferrite. So, this idiomorphic ferrite which forms inside a ferrite gamma grain will be very rarely observed, because that requires nucleation event also. So, therefore, these two ferrites are commonly observed. Now, let us look at what happens to, so let us see that how does it look like even. So, as you see here, this is basically typical structure of a hypo-eutectoid steel, and you see this is the pearlite, and in between that you have a alpha ferrite grains are present on these sides, as you see here. Basically, this is about 0.2% carbon steel, that is why the pearlitic polymer fraction is low. And pearlite, if you zoom it up, it will look like a lamellar structure, as we discussed long back. On the other hand, if I have a hyper-eutectoid steel with a carbon concentration more than 0.778%, you will have pearlite in the grains of the gamma. At the grain boundaries, you will have discontinuous cementite. As you see here, they are actually cementite crystals, they are joined separately like this, okay, and they are present along each grain boundaries. But remember, the volume fraction of eutectoid cementite is very low. That is also understandable from the phase diagram. If you do the proper calculation using the phase diagram, you will find that pro-eutectoid cementite volume fraction would be of the order of 5 to 10% as compared to the pro-eutectoid ferrite. So, that is why this volume fraction of cementite is normally low. But nonetheless, because cementite is a hard and brittle phase and it nucleates and grows on the grain boundaries of these prior gamma grains, this will make the steel very brittle. That is why the steels of carbon concentration more than 7% are used only for very specific purposes like knives, blades, or some other things which does not are actually not a structural applications, because there you need a very hard and strong material, but you do not need a good ductility. That is why they are used. So, normally blades which you use real purposes, they actually have a carbon concentration more than about 1%, 1 to 1.1% carbon is used in the steels. There you have a hard cementetic phase at the grain boundaries present along with pearlite in the grains. So, because of these cementite present in both in the pearlite as well as on the grain boundaries, it becomes very hard material, but at the same time it is also become very brittle, because the brittle phase is lining along the grain boundaries. So, that is about the pro-eutectoid phases in the hypo and hyper-eutectoid steels. Now, let us look at what are things it can undergo transformation. That is, I am going back to the original lecture. So, as you know, austenite, if I start with the austenite, which is a FCC solution of carbon and iron, slowly cool, it will transform to pearlite. That is as per the phase diagram which is seen, and it is basically diffusion control phase transformation. Why? Because this requires diffusion of carbon as the most important thing controlling the phase transformation. If you quench in water, you will have martensites. So, that is a completely opposite side, that is, it does not require any diffusion of any either carbon or anything. And in between, if you quench to intermediate temperature and keep it there for long time, you will have a new phase known as Bainite, again by the name a famous scientist E.C. Brain. And as you see here, this is a typical Bainitic structure. It is very difficult to say whether transformation is diffusion control or diffusionless. It basically can have both the characteristics. So, still a debatable question in the literature. So, first we will discuss about the Bainitic transformations. As you know, Bainites actually specifically consisting of same phases as a pearlite. So, that means it consisting of both ferrite and cementite, but morphologically and crystallographically distinctly different from pearlite. Let me just give a brief introduction. Suppose if I take a steel of say let us say about 0.6% weight % carbon and directly quench from 950 degrees Celsius temperature to about 400 degrees Celsius temperature, this remains supersaturated. Okay. Or if you want, let me just go back to the phase diagram and explain you again. Yeah, here it is. So suppose if I take about 0.6% carbon steel, and if I directly quench from 950, this is somewhere 950 here to 400 degrees Celsius temperature here, okay, it should transform into alpha ferrite as a pro-eutectoid ferrite and pearlite, right, as you have seen the microstructure. But if we cool it slowly, then only it can happen that way. Suppose we are quenching the steel from 950 to 400 degrees Celsius temperature in one go and keeping there in a bath, in a basically fixed temperature bath for long time, sometimes maybe 2 days, as long as that, then it will lead to formation of bainites. Okay, depending on the temperature to which the steel is quenched, it can lead to two types of bainites. One is known as upper bainite, which can happen at a high temperature like about 350 to 450 degrees Celsius temperature, or it can be lower bainite, which is basically nothing but a bainite which forms at between 350 to 280 degrees Celsius temperature. So whatever is the situation, bainite is nothing but a mixture of again ferrite plus cementite, but distinctly different from pearlite. It does not look like pearlite morphologically, it does not form with the way pearlite forms, and not only that, crystallographically distinctly different from that. As I said, the first thing we will discuss is the upper bainite, which forms at a high temperature. Upper bainite, these two pictures shows two different morphology. Upper bainite actually basically a phase is consisting of alpha plates, and in between the alpha plates you have what is known as Fe3C precipitated. That is why you see these are the alpha plates, okay, red color things which I am marking, these are the alpha plates, and in between the alpha plates these are actually these things which are precipitated. You see here the black color stuff here and there, they are actually cementite. So that means what? That means if I have to draw the microstructure, suppose if I have gamma 1 and gamma 2 grains, and this is a grain boundary. So what will happen? We have quenched the steel to a temperature about suppose 400 Celsius temperature. So at the grain boundaries of gamma, alpha plates or alpha basically needles actually will shoot out, like I have shown you just now for a pro-eutectoid alpha, they will shoot out and they will grow very fast. Why? Because driving force is very high. You have given sufficient large undercooling to the steel, to the basically alpha to gamma iron has been quenched. So from 727 to it has gone to 400, that means 327 degree Kelvin is the undercooling. So large undercooling means the growth rate of alpha plates or the needles which are forming from the shooting from the grains boundary of gamma will be very high. As you see here, the way I have drawn with this alpha ferrite grains or the plates have fixed oriented relationship with the gamma 1 grain and no oriented relationship with the gamma 2 grain. That is why they are growing inside a gamma 2 grain. Now once they grow, what happens? Alpha has almost no carbon and it is growing into a supersaturated gamma phase. Because they are going to supersaturated gamma phase at a very high speed, so they are rejecting the carbon into the nearby gamma. As they reject the carbon concentration in nearby regions will be increasing very high. Initially it was supersaturated gamma grains, but then alpha forms, and these alpha grains has no carbon inside it, because alpha as per the phase diagram it has almost 0% carbon. But although this is a metastable phase transformation, it may not follow exactly phase diagram, but whatever is the case, alpha will be containing very less amount of carbon than the gamma phase. So because of that, the excess carbon which is there will be precipitating as a carbide on the alpha grains basically, okay, on the boundaries of the alpha these needles. That is why it will look like this. That is what I am drawing here. You see, this is how the cementite will nucleate and grow on the sides of the alpha plates. This is a typical structure of upper bainite. This is what you have to understand. How the transformation happens? Transformation basically happens in the way that when the undercooling is very large, nucleation of alpha is very easy because undercooling large means driving force for the nucleation and growth is high, and as soon as the steel is quenched to 400 Celsius temperature, these alpha needles will shoot out from the grain boundaries of the prior gamma grains, and this is how they will grow, because their growth will very fast into the gamma grains, undercooling is high, and leaving behind the supersaturated gamma, from which then even Fe3C can precipitate out. This is not same as pearlite, please keep it in mind. Pearlite has parallel lamellae of alpha Fe3C. To be making you sure, the pearlite looks like that. You see the picture here, pearlite looks like this, it has a parallel lamellae of cementite and alpha. But on the other hand, here cementite is precipitated on the boundaries of the alpha needles, therefore these are not same. So that is what actually happens for the alpha, and these alpha actually are same thing like Widmanstatten alpha. They are not like the electromorphic alpha, they are actually looking like Widmanstatten alpha plates or alpha needles, whatever way you can call. Many people say needle or plates. The difference between is that morphologically they look similar, plate as a third dimension quite thick enough. Now as you quench the steel to lower temperature, okay, if I quench the steel to about 350 to 280 degrees Celsius temperature, then I will have a new morphology known as lower Bainite. What is lower Bainite? Again, lower Bainite is similar, like consisting of a alpha sheath or just like alpha leaf. Okay, this is alpha leaf, you see here, just like a tree leaf, it looks like alpha leaf. Obviously undercooling is larger even here, because it is undercooled to a larger extent. These alpha leaves will be shooting out from the gamma grains boundaries, gamma grain boundaries, and grow inside the supersaturated gamma very rapidly. So therefore alpha leaves will be growing, okay, they become actually much like a, these things become like a more like a tree leaves structure, and they actually grow like very fast like this, okay. So but what actually happens is that the alpha leaves which are growing inside the gamma will be having a similar carbon concentration as just like a gamma. So it has a characteristic like a massive transformation, but it is not truly a massive transformation, because composition is not changing, only FCC gamma is changing to BCC alpha. But alpha cannot hold such a high amount of carbon, right, because alpha has solubility limits of carbon in alpha is very low compared to gamma. So what will happen to those excess carbon? Those excess carbon will then precipitate inside alpha sheets, less like that. So therefore you have a discontinuous precipitation of Fe3C inside this alpha leaves actually. So these are Fe3C and this is alpha leaves. Okay. So that is exactly how this lower Bainitic transformation happens. Very evident, very clear that because the Fe3C precipitated inside the supersaturated alpha leaves, therefore this is distinctly different microstructure compared to the pearlite or compared to even upper Bainite. Remember, crystallographically this is also different. When in pearlite both Fe3C and alpha grows, they will have a distinct orientation relationship among them, but they may not have any orientation relationship with the prior gamma grains. But here they will have orientation relationship with the prior gamma grains. Similarly, look at this one, upper Bainite, the way I have drawn. The alpha plates or needles, they are shooting out from these grain boundaries. So therefore these things will have a distinct orientation relationship with the gamma 1 grain. On the other hand, they will not have much orientation relationship, specific relationship with the gamma 2 grain. But when again cementite precipitate on the grain boundaries or the boundaries of the alpha needles, there will be again orientation relationship between cementite and alpha. Here obviously same thing, gamma 1 and gamma 2, you see here the alpha will have specific relationship with the gamma 1, okay, and then cementite precipitate inside these leaves. That is what I say they looks like a leaf. If you look at a leaf structure, they look like this, tree leaf structure will be like that. So, same thing happens here, these are similarity with these. The way the discontinuous precipitation of the Fe3C happens on the alpha leaves will be like that. Many people call this actually basically plates of alpha, and the upper Bainite is known as needles of alpha, okay, or laths of alpha. There are different kinds of misnomers in the literature. So, let us call it alpha leaves in case of lower Bainites and alpha needles or plates in case of upper Bainite. That is better definitions as far as the morphology is concerned. So, that is the way transformation happens. Now, let me take you to few of these micrographs which can show you the things. Left one is basically upper Bainite. You see here these you can clearly see that alpha needles, you can see that, and within which cementite has the alpha needles, and at the boundaries of that cementite has precipitates, you can see here, that is okay. And here these are actually lower Bainites, that is very clear. This is a sheath, this is a leaf, and inside which these are actually cementites precipitate out. Okay. I think I will have some more picture for you. Yeah, this is upper Bainites, that is what is seen here, that these are the alpha ones, and between these are the actually cementites. You see between the alpha plates, this is taken from the home page of Professor Badesia, that is given here. Okay, you can see that this is a long alpha plates or needle, and there are many actually, and in between that we have this one, this is this one I draw, this is a thing, and in between that this precipitates happen, this is another one, okay, I draw, okay. Similarly, or rather it is very easy to see here, okay, this is actually needle, and on the sides of the needles you have precipitations of the carbide phase. But the one which is lower is shown here, this is just like a leaf, you see this is just like a leaf, okay, big Bainitic plates, and in between the leaves you have cementite precipitates form. That means the way they have formed is distinctly different. Alpha grown like a supersaturated alpha without no ejection of the carbon to the nearby gamma. So, all these alpha leaves have grown like that. Then because it has a lot of supersaturation of carbon, and the cementites are precipitated later on from this microstructure. So, that is the important aspects of Bainites. So, Bainites do form at the intermediate temperatures, and they have a very distinct morphology and microstructures as compared to Pearlite. They are not same, you have to remember that. So, that is what something people forget, and it is in fact at upper Bainite when it forms at high temperature, it is very difficult to distinguish upper Bainite and the Pearlite which forms at lower temperatures from the optical or SEM microstructures. Very difficult to distinguish. In fact, it is almost impossible to distinguish because they look like same. They look like these alpha plates, alpha needles, and the cementites. Cementite would look like a discontinuous, okay, here, but you can also see that cementite in Pearlite can be broken also. Buccal lamellar cementite is also present. So, we are normally get confused with the morphology of the upper Bainites, and that is why you need to look at is crystallographically in under transmission electron microscope, look at what the kind of crystallography co-interest relationship it has with the prior gamma grains or with the cementite, then only you can clearly say this is a Bainite or not a Pearlite. Okay, so but lower Bainites is distinctly clearly visible under microstructure because it has precipitation of the Fe3C inside these supersaturated alpha grains which have shoot out from the gamma grain boundaries. Okay, so therefore I will just stop here for the Bainitic discussions. In the next class I am going to discuss about martensites. Remember, martensites are very important because they are the hardest phase in the steel microstructure, and we use these martensites many applications.